Welcome back. I've been working on AutoCoders for a good while now, and I've got to the stage where eventually I'm beginning to get some decent results. So I want to tell you a little bit about the theory of how I'm actually doing it. But first, some demos. Let's run the program, and we're using QN3 coder with 30 billion parameters, although it's only using 4 billion at a time. Write code to simulate and animate the Lorentz attractor in 3D. Use sigma equals 10, rho equals that, beta equals 8 upon 3. That's to do with the Lorentz attractor. Show the chaotic trajectory evolving over time with a trail effect. Make it interactive so you can rotate the view. It's quite tricky. So now I've run it. We have to wait, and it knows where the cache directory is, and this particular model takes longer because it's 30 billion parameters, only running 4 billion at a time, he said. Oh, here we go. Wow. Quite impressive. It doesn't adjust in 3D, but is in 3D. I think we were asking it to be. Let's see what sticks to that. It's decided that's enough, and it's not going to give us any more. So let's take another example. Write Python code to produce an animated sine wave on tkinter. That's the window. It's like this. That varies from 100 Hz to 2 kHz on a plot, and the sound comes out the PC speaker using win sound, play sound, or similar. I'll just a comma there. Here it comes. It's installing sound devices. It's not doing very well here. It's it's doing. Oh, actually, it is doing something. Oh, there we go. It's the different frequencies. I wonder if it'll accept that or whether it'll keep going. I don't think it's accepted that as a solution. I think it's still going. That looked like it was aliasing, perhaps, or it's just the way the graph was being shown, but it was actually playing out the sine wave. Here it comes, second go. Made some errors here, so that's no good, so they'll have to correct these. So it's got some matplot stuff. It's got some graphic stuff wrong. Hopefully it'll fix those. It's got an attribute error here. It's just a graphical thing. There we go. How about that? It's not changing the frequency of the graph, but it's giving the audio out. It's quite nice. So it's definitely got the frequency right. It's got the hasn't got this time. It's not got the graphics right. What I should do is I should have put a slider control. It's doing it automatically, which is probably not a good idea because I didn't specify. So I'll put that down to my fault. I think it's finished now. We'll see in a second whether it's finished or not. I'm not sure if it has. I'm going to add to this. Oh no, it's still going. Here's another one that's not working at all this time. There's no audio. So what I'm going to do is I'm going to copy this start again, and this time I'm going to be a bit clearer about what I want. Oh, let's type it in by hand. Right, tkinter application that has slider control for a sine wave that varies from 100 Hertz to, let's make it 5 kilohertz. Draw the sine wave on the tkinter page, so making it much clearer this time, so it's not, doing its own stuff, so to speak. So if you're not careful, you can end up with the wrong thing. So last time I was trying to do it automatically, just varied it, which is what I asked for really, but what I really want is a slider control. Make the sine wave audio using wind sound or similar libraries. Gives it a bit of choice. Let's run. It's misspelt similar, but with LLM, large language models, that doesn't really matter. The one thing they do know is how to speak the language. Here we go. That's more like it. Perfect. To 5 kilohertz. Can't complain. That's the code here. Waveform generator, this is a better one than the one I showed you earlier. It's really cool, this one. I can select sine wave, whatever. I can select, say, a square wave, triangular wave. So I did that one. Did that one this morning, 223 lines of code, and what's more, I got it right in one shot as well, which was even more amazing. Bouncing balls. Again, this may not be the same large language model, I'm just showing you examples. A ball bouncing, it's not got a noise, a sound associated with it, unfortunately. 3D cube. They're all kind of mathematical things. Rotating cube, that's using matplot library. I've shown you some of these before, so I'm not going to show them again. Here's another 3D cube. What's this one got? Oh, that's a bit faster, that one. It's rotating. Another chaos one. It's a bit like that was a bit like the one we just did, but earlier. Cube. I don't know what that does. Oh, it's just a surface plot of a cube. These are using other models. Close Encounters, the third kind. Plays in. Which is quite funny. A cone. Might be. Oh, okay, nothing special there. got a Kalman filter there. Phase lock loop. Oh, okay, that's tracking. That's because it's not a type 2 loop. That's the output, and that's it's trying to follow it. It's got a velocity error if you're into control systems. Recursive least squares, I don't know if you know about that, but that's used in various self-tuning filters and adaptive controllers and so on. Estimating a second order system. It's driven by white noise. That one worked. Oh, and there's the signal, the output of the time series. It's quite a small program. This is the cubed root of a number using Newton's method, the conversions. It's quite nice actually, this. So the cubed root of 27 means it's finding the solution to x cubed minus 27 equal to 0. And it shows the initial guess and then how it's converging to 3, which is the cubed root of 27. It even shows you how it works with the gradient there, which is rather nice. This was using, again, wasn't using the current model I talked about with, what was the current one? 40 billion parameters. Goodness me. A rectification one, what's that? Is that? Oh, it just shows the average value of a fully rectified sine wave. Breakout. Might have seen this one before. Unfortunately, there's no sound effects with that. It only gives you one shot. But bouncing sphere. Oh, that's using matplot library rather than Pygame. It's quite good actually. This will be a Fourier series. Yeah, Fourier series, 10 terms. I cubed using OpenGL, which is a bit different. Really nice. Okay, now the demos are over. What's an autocoder? So an autocoder writes code in a chosen language from a prompt. In this case, we're using Python. So, for example, the prompt might be write code to simulate a pendulum and show the graphical output. This simple one. Now, this is not going to do code, thousands of lines for many reasons. First of all, these are small, large language models we're using. We could extend it to bigger ones, but the method I'm using here rewrites the whole code every time it does it, so not very efficient. If you had thousands of lines of code to have to write it out every time, you would do it in blocks, which requires a little bit more careful thinking. So what I wanted to do with the autocoder was ultimately make it so that it's offline, so you don't have to pay for internet connection or any subscriptions to large language models or anything. So of course you can use a large language model and then that's your problem solved, I guess. You don't need to use this. The only thing is it would be a little bit different in that it won't run, the large language model won't run the program. You'll have to then copy it and install the libraries and run it yourself, which is no big deal, of course. It's quite simple to do that. But this does everything for you. So it installs the libraries, does everything. Otherwise, you pay a monthly fee or something. There's a few LLMs that don't, but if you want the really good one like Claude, you have to pay for that. Otherwise, you get a little bit of time and then it times you out. You get strung up with it in the sense you get into it, and then it says, "Oh, well, you've run out of time, and you have to pay if you want more." So, anyways, Claude is brilliant anyway. So if you do want to use it, so this will run entirely offline. So this is what I was using initially, the ideal AutoCoder, just assuming that all large language models are equal and they're all brilliant at programming, which is not true, of course. So it assumes a properly trained large language model is good at coding. What you do is you write the prompt and it outputs the code, and that's it. And if it makes an error, you just feed the error back into the AI the next time round. It's like a loop. I've written it like a control system rather than the usual sort of computery science type thing, how they do it. It's a bit more like a control system, left to right rather than up and down, which is what they use. So it relies on the large language model knowing the language and errors in the training. And if it knows that, then you don't need much else actually. You're laughing because if it comes up with an error, say, "Oh, I know what that error is," and corrects it and succeeds, and that's your problem solved really, and you don't need anything more than that. Of course, in real life, the large language model makes mistakes. So what we can do, it's the most obvious thing to do, is here, I hope you can see this, yeah, is we've got the code prompt going into the AI, and I've disconnected this part for the moment, and let's assume that it creates an error, and after 3 repeated errors of the same type, it can't solve the problem. And that does happen with some of the large language models, particularly the ones that are not designed specifically for coding. So what you do then is you do an internet search, and then it hopefully gives it information which you feed back to the AI, and then it can fix itself, and then you get success. Sometimes it doesn't, and that's the end of it. You just can't do any more. But while you're at it, why not just save that error in a JSON file, call it the error cache, and then we'll use it again at some point. So the next level up is we have enough errors from our internet searches, and we've got some kind of error cache. So in the future, we don't have to do the internet search because we've got this error cache, and we correct ourselves by look. So we always have to look up the error cache first if we make an error, and only if it's not in the cache. In other words, if it's not a hit, we call it a hit. If it gets that, if it's not a hit, then it has to do another search and find that. So I was looking at this when I was doing it, and I thought, God, it's got to keep on looking at the internet every time, and God knows how many errors there's going to be. It's going to have to, go on for a long time before I get a decent error cache. And the error cache was quite a basic error cache as well. It was just, a couple of links and things. It wasn't actually much information. So then I thought, if I've got a particular language, like say Python, there's only a finite number of errors you've got. I mean, whoever wrote the language wrote the errors. I mean, so there's a syntax error, for example, is the most common one in all the languages, and you know what that is. It's something misspelt or something. There's an indentation error. Mind you, it would probably know those errors because these are quite basic errors, but there'll be a whole load of other errors all based on different libraries. And I thought, based on the libraries that I commonly use, why don't I just artificially create the errors, and then I can fill the cache up beforehand. And I call this seeding. Preset. Well, what was my name? I think it was my idea to do this, and I think the AI that was programming it called it seeding. Maybe it's an idea that's used a lot, I don't know. Maybe not. So you put in the error seeds, and then you do an internet search. The AI itself uses the same AI usually, but it doesn't have to be. It can be a different AI. And then the internet, the AI summarizes the result you get from the internet and sticks it in a database, a JSON database, and that gives you your cache. So typically this took a couple of hours to go through God knows how many libraries, and I thought it was never going to end, but I eventually ended up with a rather nice database, and it was detailed as well. It wasn't just a couple of lines, it was paragraphs of information, and meaning that in future I don't need to do the internet search. So I modified it. Forget this for the moment. So I've got the code coming in here, the prompt rather, code prompt, into the AI. If it's successful, great. If it is an error, then it goes into the seeded error cache. So hopefully, the solution will be in there of the error, because I've already preceded all the solutions. So if it's a hit, then feed it back to the AI and correct itself, and then hopefully the next time round, the next iteration, it'll be a success. If it's not a hit, then you're in trouble. I mean, it'll either stop or do it 3 times and you can't proceed, but usually it is because I've preceded all the error cache. The other thing I added, this wasn't my idea, this was Matrix X, ChatGPT's idea, to put planning into it, and to use the seeded error cache which I already had as part of a planning. So before you start a job, you don't just go straight into it, make a mistake and then correct yourself, do you? So you plan it first, you plan it ahead. And so whichever libraries you're going to use, you have a look in this seeded error thing and say, oh, okay, so these are the kind of things I would expect, and these are the kind of errors I might expect if I was going to use these libraries, because I already put them in there. So that information is fed into the AI, and for success, fine. If it still makes an error, then it goes into the seeded error cache and so on. Now, I just added one more refinement. I mean, you can keep going. And that refinement was lessons learned. I had this thought that large language models, in case you don't know, surprisingly don't actually learn anything. I mean, they learn when they're training. They're not a problem with that. But obviously they can't learn everything unless they're specific to various tasks. It depends on how much data they've fed into them, and so a large language model can't be expected to know everything. And it's also time dated as well. It was, it might have been a year ago or whatever when it was trained, so a library might have changed in that period of time, so it can't be expected to get everything right. But they tell us if you tell it what it is, if it can do a search and find out what the error is that's maybe not in your cache, then you're still not much better off, because you're okay that time, but then the next time it's forgotten again because it's not got a memory. And in case you're thinking, well, why don't we just add all the information we've got? Why not just feed the whole error cache, for example, into the AI? If you could do that, they would take up all the tokens, so you'd have nothing left to do the AI part. So you can't just feed data in. But what you can do is you can have a little database of lessons learned, if they're and not load all of them in. Of course, you just have a look through it and say, these lessons were learned before, the mistakes I made at previous iterations, previous times, and I'm going to use them again along with the planning. So you still use your planning, you use your lessons learned, and go around the loop again, and that's it really. So this enables us to look at what's in the cache at the moment, which is generated automatically for various errors, all these errors here. So rather than making the errors and then having to look them up, I preempted things and said, let's assume there was these errors. What would you do? And then it's got a database of how to fix things, so it knows this. So there's a whole list of things it can go through, which is a lot to us, of course. If I'm looking at that, I'm going, oh my God, look at all these different things. But for a large language model, it can do that in a second or something. So all these different, so if I want, I can add new ones by selecting, let's say, indentation. Well, indentation error is a bit simple. It should be able to fix that on its own. If it can't fix an indentation error, then it's not much good. Say a permission error with MATLAB. Oh, let's say NumPy, which is a numerical thing, and the query, and then I search for a solution, and it gives me the details, and then I can add it to the cache, and that's the simple, the manual way of doing it. That's not how I created all these. Otherwise, I would have been there all day doing it. And the same for lessons learned. There's a lessons learned manager where we can, it's very similar, and we can put a task in, task type, let's say control systems, machine learning, or whatever, image processing, error type, import error, index error, and so on, and the libraries used, and the error snippet, and the lesson that was learned, so that it hopefully shouldn't make that mistake the next time.